Let's discuss different types of DC generators as it is listed over here. We have main three types: separately excited generators, shunt, and compound generators. And the types of generators are based on where the field winding is located, the flux, the field flux where it is coming from, where that winding is located. In most of the generators we use electromagnet. Some generators can be permanent magnet, but most of the magnets, they are electromagnets. So the location of that electromagnet basically defines the type of generator. So separately excited generators, as you can see in these two figures, this is the electromagnet which is around the armature, and this electromagnet is connected with a separate power supply. So this power supply is sending current to just the electromagnet to produce the flux. It has nothing to do with the armature arrangement. So it is kind of separate from the armature. Hence, it is called separately excited generator. Excited means that it is being excited by the flux which is produced by the current from a separate power supply, DC power supply in this case. This is the circuit diagram right here. So this is your field connected to VF, the power supply, which will produce the flux, and that flux is going to be interact with the armature winding. And since armature is rotating with some velocity, Faraday's law is going to come into effect, and the voltage will be induced in the armature. And when there is no load connected, of course, whatever voltage is induced is going to appear between the terminals of the generator. But once you connect the load, then current will start flowing here, and the voltage at the terminal is going to be different than the voltage that is induced, because some voltage is going to be dropped in the winding of the armature. R0 shows the resistance of the winding of the armature. Generally, this resistance is extremely small, 1 ohm, 2 ohm, perhaps even smaller, and ET and E0 are quite close to each other. But again, it depends how much current is flowing through the generator. If the current is very heavy, let's say if it is 100 ampere current, and if R0 is even half an ampere, that means a 50 volt drop is right over there. So again, it depends how much voltage is dropped here. ET and E0 can be very different based on how much current is flowing through the generator and what is the value of R0. But in general, at full load, I think they are about 10% different, not more than 10 to 15% maximum. They are different. So this is separately excited generator. And how do you change the direction of the induced voltage? Right now the voltage is induced such that positive is on top, negative at the bottom. So to change the direction of the induced voltage, you can do two things. Either you can rotate the armature in the opposite direction, or you can connect this power supply, the field power supply, in the opposite direction such that the flux direction that is linking with the armature is going to be in the opposite direction. So either one way can be used to change the direction of the induced voltage. If you change both of them, that is, you change the power supply direction, this power supply, and you also change the direction of the rotation of armature, then E0 will still be induced in the same direction. So we don't change both of them at the same time. Only one can be changed to change the direction of the induced voltage. This is a graph that shows how much field current has been supplied versus the induced voltage. And again, since we are looking at the electromagnet, and every magnet is going to be all the poles in the magnet, all the dipoles in the magnet are going to be aligned at some time. So basically it's going to be saturated. So as you can see over here, initially the magnetism is still increasing, and the induced voltage is still increasing because it depends upon the flux that has been produced by the magnet. Eventually, as you keep increasing the field current, it will start saturating, the dipoles will start having alignment, and it starts saturating. It's not going to increase as fast as it was increasing initially. So somewhere around the knee of this curve, you have the rated voltage, about 120 volt, DC voltage, and um, based on how much flux is being is being produced through the field, you can find out how much induced voltage is there. So again, as we discussed, no load terminal voltage is going to be the same as induced, and when it is running at full load, then the terminal voltage is going to be about 5 to 10% different than the induced voltage, because some voltage is going to be dropped in R naught. Go over this 4.1 example. It's pretty straightforward example. You're using voltage division to find the terminal voltage in the presence of the load, so you will understand it. It's pretty straightforward. Shunt generators, next type of generators. And shunt generators, basically the winding is in parallel with the armature. That's why it's called shunt generator. The field winding is in parallel with the armature. So that's one thing. The other thing is you don't need any extra power supply to supply current to the field to produce the flux. And that's perhaps one of the biggest advantage of using shunt generator. That is, you don't need any extra power supply. So how do you produce flux in a shunt generator? It's a very interesting phenomenon. All right, so this is a circuit diagram, and this is the cross section of the generator. So what happens is, let's go back to chapter number 2 when we discussed hysteresis, and we discussed that when a magnet is magnetized, when an electromagnet is magnetized or a magnet is magnetized, and you remove the magnetizing force, you remove the MMF, you remove the current that was producing the magnetism or flux, the dipoles do not misalign. There is still some alignment left in there. So even though you remove the current, you remove the magnetic field, but you don't lose all the magnetism in there. There is still some flux that is left. That we studied under the hysteresis phenomenon in chapter number 2. So the same thing we are going to use for our advantage in the shunt generator. So what happens is, when you create a shunt generator, basically you energize the coil field, and then of course you remove the supply, so it will de-energize, but again there is some magnetism that is left in that electromagnet. So when you crank your armature, when you move the armature using a mechanical input or turbine, then some because there was a little bit of flux in this shunt field. Let me just use my hands. So there's a little bit of flux, weak flux, that was linking with the armature, right? Now this little bit of flux interact with the armature that is moving clockwise or counterclockwise, and again, according to Faraday's law of electromagnetic induction, whenever there is a change in the flux, voltage will be induced. So voltage is induced over here, and that voltage is not very high, because again remember, flux is not that strong. It is a weak flux. But whatever voltage is induced, that voltage start running a current. Right now assume there is no load connect. So that voltage start running a current. Now when this current goes through the shunt field, the electromagnet that is in the shunt or parallel, then your magnetism, your flux, it increases. So now you are increasing the amount of flux produced by the shunt field, because current is running through the shunt field. However, the current is weak. Now since the flux is going to increase and it is still linking with the armature, the E0 value is gonna go up. Now this higher E0 value will run higher current, and again that higher current is going to produce higher flux. So this process will keep on going until saturation will happen, and E0 is going to be whatever is the rated induced voltage in the shunt generator. So that's how voltage is induced in the shunt generator. We don't need any external source. That's a big, huge advantage of shunt generator. Okay, so now let's see what I have. Okay, so controlling the voltage of the shunt generator. How do you control the voltage of a shunt generator? If you put a rheostat, a variable resistor in the field, that is, you start controlling the current of the field. Then of course, controlling current means that you are controlling the flux. So if you increase so let's say you have a base value of the resistor, and then that base value of the resistor is producing some voltage. I think I have a graph here, right here. So let's say you have a base value of resistor which is R1, and since you can apply Ohm's law over here, then E naught over R1 is going to be Ix, which is the base value of the current. We are basically adding both the resistance of both this external resistor and the resistance of the field, and we are calling it, let's say, R1. So when you apply Ohm's law, you will get V is equal to R1, or E naught is equal to IF R1, and you're gonna get a straight line with a slope of R1. And then if you use the curve that we discussed earlier for the separately excited generators, you plot that curve as well, E naught versus the flux which is produced by the current. And of course, you saw that initially it's going to increase linearly and then it starts saturating. So wherever these two lines are going to intersect, basically that how much voltage you are generating. So let's say your base value is R1 120 ohm. So you're generating about 120 volt of voltage. Now if you want to generate higher than that, you reduce the amount of the external resistor below the base value, which was 120 ohm. So let's say you go to 50 ohm, and then the slope of this line becomes lesser. Basically you're putting more current in the field, which will produce more flux, and that will result in higher voltage. So this will be the voltage, 150 volt. And if you want to decrease the value of voltage, then of course you're going to increase the value of resistor. Now you cannot just keep increasing the value of resistor, because observe this line. If you keep increasing the value of the external resistor, this resistor, what's going to happen, that at some time that line that you are creating using Ohm's law is going to just become parallel to this curve. And when it will become parallel to this curve, basically your voltage induced is going to drop down to zero. There is no voltage that will be induced. And it makes sense, because if you keep increasing this, that means you keep reducing the current. And at some point, the current is just going to become so weak that the flux produced by this field resistance is just not going to be able to reach to your armature. So it's just going to be very, 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 very weak flux, and it's not going to reach to the armature. Hence, no voltage is going to be induced in the armature, no matter how much you rotate the armature. So that's what it shows over here. Anyways, so let's come down to the effect of when you connect the load to the shunt generator. So in the separately excited generator, we saw that when you connect the load, some current starts flowing in the generator, and your terminal voltage is different than your induced voltage. Some voltage is dropped in your armature resistance. Alright, so now when you connect load over here, this load, what's going to happen? Load current will start flowing, right? Now when load current will start flowing, the voltage will be dropped in the armature resistance, R naught, right? Now when the voltage will be dropped here, that means the voltage across the shunt field, let's say, let's call it, it's a terminal voltage, so this is VT still. So this voltage is going to drop. Drop means that it's not going to be the same as it was before. Now when that will happen, that means the current in the shunt field is going to drop according to Ohm's law. And when the current will drop, the flux will drop. When the flux will drop, the induced voltage value itself is going to go down. So there is a it has, I don't know how to call this, but a two-way effect, let's call that. So there's a two-way effect of the drop on the terminal voltage in the shunt generator. One effect is the terminal voltage is going to be different than E naught, because some voltage is going to be dropped in R naught when IA will increase, because it has to accommodate IL. The second effect is going to be that it's going to go even smaller Because the induced voltage itself is going down, right? So in the separately excited generator, the only thing that affects the terminal voltage is how much voltage is dropped in the armature resistance. E naught was still the same, irrespective how much current is coming out of the armature. Here, that's not the case. E naught itself is going down because your shunt field current, your terminal voltage is going down, and your shunt field current based on the terminal voltage. So the full load to no load terminal voltage in the shunt generator is even smaller than the separately excited generator. So that's a drawback. The plus point again is that you don't need any external source to run the shunt generator. It's all in there. You have the residual flux in the shunt field. That residual flux is going to generate some voltage, that will run some current, that will generate even higher voltage, run some current, and so on and so forth. So there's an advantage and a disadvantage. Effect of load, as I explained, it's about 15% less than no load voltage, more than the separately excited. Go over example 4.2, straightforward example. Okay, so the third one is compound generator. That's a compromise between separately excited and shunt generator. So what is the advantage of shunt generator? That the terminal voltage under load does not drop as much as the terminal voltage of shunt generator. What is the disadvantage of separately excited? That it requires an external source to produce the flux. Now, in compound generator, we have two fields. One field is in the shunt, as in the shunt generator, and one field is connected in series with the load. So if I go back here, so one field is the shunt that you see, and the other field is going to be right over here. This is going to be another magnet, another electromagnet. Oops. So both can provide magnetism. And based on the direction of both the fluxes from the series and shunt field, there are two categories of complex compound generator. One is differential, when both fields will cancel each other, and one is cumulative, when both fields, flux of both fields add to each other. So how does it operate? When you have no load connected, it operates exactly like shunt generator, because there is no current that is going through the series field since there is no load connected. Let me see where's the circuit diagram. Right here. I think the other circuit diagram is better. Anyways, they're not showing, I'm not showing any armature resistance, but if there's an armature resistance, that's going to be here, right here, right? So if there is no load connected, if this is infinity, if this is open circuit, then the current is going to come out, go through the armature resistance, go to the shunt field, and the terminal current, which will be here, these are the terminals, oh sorry, these are the terminals. The terminal voltage is going to be the same as the induced, not the induced voltage, it's going to be the same as the voltage across the shunt field, because again there is no voltage drop in the series field, there is no current flow. Okay. Now the disadvantage again, remember, for the shunt generator is when you connect the load, current starts flowing, and first drop is across the armature resistance, which drops the voltage across the shunt field, which draws less current in the shunt field, which will produce less flux, and then induced voltage itself goes down. Okay, so what's going to happen over here when the current starts flowing? Now the current starts flowing through the series field when you connect the load. Now, if it is a cumulative compound generator, that means now this series field is also going to start producing flux. And that flux is going to add up to the flux of the shunt field. So, in compound generator, the total flux under the load is not going to go down as much as it was going down in the shunt generator. In fact, it is possible that it may even remain the same. But let's assume if it is going down, the sum of these two fluxes is still more than what it was in the shunt generator under the load. So what's going to happen, that since your flux is higher, your induced voltage is going to be higher than that, and your terminal voltage is not going to go down as much as it was going down in the shunt generator. So that's one of the uh, advantage of using compound generator. Compound generators are used very frequently, very commonly, because again they are a very good compromise between pure shunt generator and separately excited generator. This is an example on the shunt generator. Make sure you go over that example, and that will conclude this chapter. You can read generator specification. It's pretty self-explanatory, so go ahead and read that. I don't really have to go over it in the video lecture. I covered all the important things, and that will help you understanding the function of generators, different type of generators, and help you solving the problems regarding the generator.